The strangest thing about the universe is not that it is enormous, but that it can be understood at all, from the first hot, dense moments to the birth of atoms, stars, galaxies, planets, dark matter, dark energy, and the quiet place Earth holds inside it all. Every part of the cosmos leaves some kind of trace. Some traces arrive as ancient light, some appear as gravity from matter no telescope can see. Some are written into the atoms that make oceans, rocks, and living bodies. Thank you for spending your time here with Calm Space Science. If this kind of slow, thoughtful journey helps you relax, study, or fall asleep, a gentle subscription or share helps the channel continue creating calm science stories. Leave a comment with the country or city you're watching from, what time it is there, and whether this is part of your night, morning, or quiet work session. The larger story now opens from the simplest question: what is the universe? The universe is not only the collection of stars seen in the night sky, it is the complete physical setting in which every star, planet, particle, field, motion, and event belongs. In the simplest scientific sense, the universe means all of space and time together with all matter and energy within them. This definition sounds broad, because it has to be broad. Nothing physical can stand outside it in the ordinary meaning of the word physical. Every galaxy, every beam of light, every atom in a living cell, every magnetic field, every wave of radiation left from the early cosmos, and every region too distant to observe directly is part of the same overall subject. The word universe, therefore, does not name one object among others. It names the whole system in which objects, distances, histories, and laws can exist at all. This is the first useful boundary. The universe is not simply what is visible, and it is not limited to what human instruments can currently measure. The visible portion is only the part from which light or other signals have had enough time to reach Earth. Beyond that observable region, space may continue, perhaps with the same general properties, perhaps with features that cannot yet be tested. Science can speak most firmly about the observable universe because it leaves evidence. The larger universe, if it extends beyond that evidence, remains a careful extension of known ideas rather than a directly mapped place. That distinction matters from the beginning, because understanding the universe means understanding both what has been measured and where measurement reaches its limit. The observable universe is centered on Earth only in the practical sense that Earth is the location from which observation is made. This does not make Earth physically central. Any observer in a distant galaxy would also see a surrounding sphere of observable space centered on that observer, limited by the travel time of light. The boundary is not a wall, an edge, or a shell where space stops. It is a horizon produced by time, distance, and the finite speed at which information travels. Light from very remote regions has been moving for almost the entire history of the cosmos, and some light from farther regions has not reached any telescope on Earth. The horizon marks the edge of available information, not necessarily the end of existence. This is why the word universe carries a quiet difficulty. It refers to everything, but science can study that everything only through signals that arrive inside one observable region. From those signals, a surprisingly coherent picture is formed. The universe appears to have begun in a much hotter, denser state, and to have expanded and cooled over time. Galaxies are not flying through empty space from a central explosion. Rather, distances between large clusters of galaxies increase because space itself changes its scale. The expansion does not happen into an outside emptiness that surrounds the universe. In modern cosmology, there is no required outside into which the cosmos grows. Expansion describes the changing relationship between distant regions of space. This idea is not easy at first because everyday experience treats space as a fixed container. A room can be entered, crossed, measured, and left behind. Cosmic space is different. It is part of the system being studied, not merely a passive backdrop. When cosmologists describe the universe, they are describing the contents and the geometry together. Geometry here means the way distances, angles, and paths behave on the larger scales. Matter and energy influence that geometry, and geometry influences how matter and light move. The universe is therefore not a stage with separate actors placed upon it. It is a linked physical whole, where space, time, contents, and law remain inseparable in the deepest description available. Even this whole is not uniform in every local detail. On small scales, the universe is uneven. Matter gathers into planets, stars, gas clouds, galaxies, and clusters. Empty-looking regions separate richer regions. Some places contain intense radiation, strong gravity, and violent formation. Other places are thin, cold, and nearly empty, yet on very large scales. After averaging over immense distances, the universe appears broadly similar in all directions. This large-scale regularity is one of the foundations of cosmology. It allows scientists to build models that are not only local descriptions of nearby space, but descriptions of the overall cosmic pattern. The claim is not that every region is identical. The claim is that the largest view smooths out many smaller differences. A universe with this kind of large-scale order can have a history. It can be described as changing from one physical condition to another. In its earliest accessible phases, the cosmos was hot enough that matter and radiation behaved in ways far removed from ordinary experience. Later, as expansion continued, conditions cooled enough for stable atoms to form. Much later, gravity amplified small differences in density, pulling matter into the first stars and galaxies. Over time, stars made heavier elements. Some of those elements entered new generations of stars and planets, and on at least one planet, chemistry became biology. This sequence does not make life the purpose of the universe. It shows that life belongs to the same physical history as stars, atoms, and galaxies. The material in human bodies was not added from outside the cosmic story. It was processed through stellar and planetary environments that follow the same laws as everything else. That is one reason the definition of the universe cannot be only astronomical. It includes the smallest measurable particles and the largest visible structures, but also the continuity between them. An atom on Earth and a galaxy cluster far away are not separate kinds of reality. They are different scales of the same physical order. To define the universe carefully is also to separate it from older or looser ideas. In casual speech, the universe may be treated as a place, a destiny, or a symbol of vastness. In science, it is treated as the total physical domain under investigation. The scientific definition does not claim that every question has already been answered. It provides the frame in which questions can be asked. What is space? Why does time have a direction? What is the origin of the cosmic expansion? Why do the physical laws have the form they do? Does the universe have a boundary? Or is boundary the wrong idea? Are dark matter and dark energy signs of unknown ingredients, incomplete theories, or both? These questions do not weaken the definition. They show why the definition is necessary. Without a whole domain, there is no clear way to connect local facts to cosmic history. A meteorite, a spectrum from a galaxy, the orbit of a moon, and the temperature pattern of ancient radiation all become pieces of one study because they all belong to the same universe. The definition is therefore both simple and demanding. It begins with everything that physically exists, but it immediately leads to limits of observation, limits of theory, and limits of language. The word everything can be spoken easily. It is much harder to examine. No telescope can look at the universe from outside. No experiment can place the whole cosmos in a laboratory. Every measurement is made from within the system being measured. This does not make cosmology guesswork. It makes cosmology a science of traces, patterns, and consistency. Light carries information about distant stars. Gravity reveals mass even when matter cannot be seen directly. Element abundances preserve signs of early nuclear processes. The faint background radiation left from the young cosmos records conditions from an ancient stage when the universe was much simpler in structure than it is now. Each clue is partial, but together they form a connected model that can be tested against new observations. That model may change in detail, and some parts may be replaced. Yet the basic act remains the same. The universe is defined as the total physical reality accessible through its effects, with the observable part serving as the evidence-rich region from which the larger picture is built. This opening definition is not meant to solve the mystery. It gives the mystery a disciplined shape. The universe is all space and time, all matter and energy, all known forces, all fields, all events, and all histories that can be physically connected. It includes the ordinary and the extreme, the familiar and the unreachable, the living and the lifeless. The luminous structures that fill astronomy books and the dark components inferred only by their influence. It is a single word for a subject too large to hold at once, yet not too large to approach step by step. The first step is to see that the universe is not merely a vast place containing things. It is the whole condition under which there can be places, things, motion, change, evidence, and questions at all. Space and time are often introduced as if they are simple background features, one giving objects room to exist and the other allowing events to happen in sequence. That ordinary picture is useful for daily life, but it is not enough for the universe as a whole. In modern science, space is not merely emptiness, and time is not merely a clock running beside it. Together they form space-time, the shared framework in which positions, distances, motion, gravity, and history become measurable. Every planet, star, galaxy, and particle exists somewhere, but somewhere only has meaning because distances can be defined. Every event happens before, during, or after another event. But that order only has meaning because time can be measured. The universe is therefore not just filled with matter and energy. It also has a structure that allows matter and energy to be located, to move, to interact, and to leave records. The first quiet difficulty is that this structure is not as fixed as it appears from the surface of Earth. On human scales, space seems stable. A road keeps its length. A room does not expand while a person walks across it. Time seems to pass at the same rate for everyone nearby. Clocks agree well enough for ordinary purposes. These impressions are not false in their own setting. They are local approximations, valid where speeds are low compared with light and gravity is not extreme. The larger universe reveals that the approximation has limits. Motion changes measurements of time and distance. Gravity changes the rate at which time passes. The expansion of the cosmos changes the separation between galaxies on scales far beyond any local structure. Space and time remain familiar enough to use, but not simple enough to treat as absolute. The key change comes from relativity, which does not remove order from the universe but makes order more precise. Light travels at a fixed speed in empty space, and that fact forces space and time to be connected. If the speed of a light is the same for observers moving differently, then measurements of distance and duration cannot remain independent in the old way. Time can stretch. Length can contract along the direction of motion. The deeper lesson is not that everything becomes uncertain. It is that measurements belong to physical situations. Time is not a universal rhythm shared equally everywhere. It is part of a relationship among motion, gravity, and the path taken through space-time. This matters for cosmology, because the universe is not observed from outside. Every signal arrives after travelling along a path through space-time. The light from a distant galaxy is not a simple snapshot in the ordinary sense. It is a record from an earlier stage of that galaxy, carried across expanding space until it reaches instruments near Earth. Looking far away also means looking back in time. Not because telescopes are magical, but because information needs time to cross distance. The sky is therefore layered by travel time. The universe is not presented all at once. It is received through delays. Gravity adds a second transformation. In the older picture, gravity was a force pulling objects through space. In general relativity, gravity is also understood as the curvature of space-time caused by matter and energy. Curvature does not mean space bends into some visible substance. It means the paths followed by objects and light are shaped by the distribution of mass and energy. Around Earth, this curvature is weak but measurable. Around neutron stars and black holes, it becomes intense. A black hole is not powerful because it is a hole in the simple sense. It is a region where space-time is curved so strongly that paths leading outward from within a certain boundary no longer reach the outside universe. Time itself is affected by this geometry. A clock deeper in a gravitational field runs more slowly compared with a clock farther away. It is a feature of time in a curved space-time. It also changes the meaning of extreme cosmic environments. Near a compact object, time, light, orbit, and escape are no longer separate issues. They are different expressions of the same geometry. At the scale of the whole universe, the geometry becomes one of the central questions. Is space flat in the large-scale sense, or curved in a way that changes the possible shape and fate of the cosmos? Measurements so far suggest that the observable universe is very close to flat on large scales, but close to flat does not mean fully understood. Expansion is the place where space becomes most difficult to picture clearly. Galaxies within a cluster can orbit and interact under their own gravity, and objects such as stars and planets do not expand along with the universe. Bound systems remain bound. The expansion appears on larger scales, where the distance between galaxy clusters increases over time. This expansion is not best described as galaxies moving away from a central point. There is no observed center from which everything began to fly outward through pre-existing emptiness. Instead, the scale of space itself changes, so that distant galaxies become more separated even when no special central location exists. Every sufficiently distant observer would see other distant galaxies receding in a broadly similar way. This does not mean Earth occupies a privileged position. It means the expansion is a property of the large-scale universe. The farther a galaxy is, the more its light is stretched during the journey, shifting toward longer wavelengths. This redshift is one of the main pieces of evidence for cosmic expansion. It turns distance, light, and time into a connected record. When radiation from the early universe is observed today as a faint microwave background, it is not merely old light. It is light that has been stretched by the growth of space since the time when the universe first became transparent. Expansion changes what arrives, and by measuring that change, cosmologists reconstruct the earlier state of the cosmos. Time also has a direction in the universe, even though many basic physical laws can be written in ways that do not strongly prefer past over future. The practical direction is linked to entropy. a measure of how energy and matter are arranged and how many microscopic states can produce the same large-scale condition. In ordinary terms, systems tend to move from more ordered special conditions toward more dispersed and more probable ones. Unless energy is supplied to maintain order locally, a hot object cools into its surroundings, gas spreads through an available volume, stars burn nuclear fuel and gradually change. Living systems maintain their internal order only by taking in energy and releasing waste heat. This direction of change helps explain why the past and future feel different. Cosmology deepens the issue because the early universe appears to have begun in a very special state, hot, dense, and remarkably smooth, yet able to produce later structure through gravity. The arrow of time is therefore not only a philosophical puzzle, it is part of the physical history of the universe. Why the early state had such low gravitational disorder remains one of the deeper questions beneath the calm surface of cosmic history. The passage of time allows stars to form, planets to cool, elements to circulate, and life to arise. But the direction of time is tied to conditions that are still not fully explained. Space and time are therefore not separate containers holding cosmic events at a distance from one another. They are part of the behavior of the universe itself. Space gives distance its meaning, but distance changes with expansion and curvature. Time gives sequence its meaning, but sequence depends on motion, gravity, and the path taken by light or matter. Together, they make the universe observable as a history rather than a frozen arrangement. The same framework that permits a moon to orbit a planet also permits light from the early cosmos to arrive billions of years later as evidence. The same geometry that slightly adjusts satellite clocks near Earth also defines the boundary around a black hole and the widening separations among remote galaxies. This unity is one of the reasons cosmology can connect ordinary measurements to extreme scales. A clock, a photon, an orbit, and a redshift all become ways of reading space-time. Yet the framework is not finished knowledge. It still presses against unanswered questions. Relativity describes gravity and space-time with great success, while quantum physics describes matter and energy on the smallest scales with equal power. The two descriptions do not yet form one complete theory under the most extreme conditions, such as the earliest moments of the cosmos or the deepest interior meaning of black holes. Space and time are the framework of known reality, but they may also be clues to a deeper layer still hidden beneath present theory. The universe can be explained slowly only by accepting this double role. Space-time is the stable language in which modern cosmology speaks, and at the same time one of the subjects that cosmology has not fully understood. Matter and energy are often spoken of as separate things, as if matter is the solid substance of the universe, and energy is the motion or power moving through it. That picture is useful at first, but it becomes incomplete very quickly. Matter is not only rock, metal, gas, dust, and living tissue. It is anything with mass that can take part in physical structure, from the particles inside atoms to the plasma in stars and the thin gas between galaxies. Energy is not a material in the same way, yet it is just as necessary to the universe because it describes the capacity for change. Energy appears as motion, heat, light, radiation, chemical storage, nuclear binding, and the gravitational arrangements of massive bodies. Without matter, there would be no stars, planets, galaxies, oceans, or cells. Without energy, none of those structures could form, shine, orbit, cool, react, or evolve. The universe is built from both, and in modern physics they are connected more deeply than everyday language suggests. Matter can be converted into energy under certain conditions, and energy can contribute to mass and gravity. A star shines because a small part of the mass in its core is transformed into radiant energy during nuclear fusion. A particle can appear from energetic conditions if the rules of physics allow it. A region filled only with radiation can still influence the expansion and curvature of space-time. The distinction between matter and energy remains useful, but it is not absolute. It is a practical way of describing different expressions of the same physical world. The simplest familiar form of matter is the atom. Although atoms themselves are not fundamental in the deepest sense, each atom contains a nucleus made of protons and neutrons, surrounded by electrons arranged according to quantum rules. Protons and neutrons are themselves made of smaller particles called quarks. Held together by the strong nuclear force, electrons belong to a different family of particles and appear, as far as current evidence shows, not to be built from smaller components. This internal structure matters because the visible universe depends on it. Hydrogen, the lightest and most common element, has the simplest atomic structure. Helium is slightly heavier and also abundant. These two elements formed in great quantity during the early hot stages of the universe before stars existed. Heavier elements such as carbon, oxygen, silicon, iron, and many others came later through the lives and deaths of stars. The matter in a planet is therefore not just a pile of atoms. It is a record of processes separated by enormous time and scale. Some atoms were formed in the early universe, others were assembled in stellar interiors, released by stellar winds, or scattered by explosions. The visible world is made from material that has passed through several physical environments before becoming rock, water, air, or biology. Energy gives this material history its movement. In the early universe, radiation was a dominant part of the cosmic contents. Matter and light interacted so strongly that the universe was opaque, filled with charged particles and photons in close contact. As expansion continued, the temperature dropped, electrons joined atomic nuclei, neutral atoms formed, and light began to travel more freely. That ancient light is still present today as the cosmic microwave background, weakened and stretched by expansion, but still carrying information from a younger universe. This is one of the clearest examples of energy becoming a historical record. Radiation does not only illuminate objects, it can preserve a memory of conditions through its wavelength, temperature, direction, and pattern. Later, when the first stars formed, energy again changed the course of matter. Gravity gathered gas into dense regions. Compression raised temperature and pressure. Nuclear fusion began when conditions in stellar cores became extreme enough for hydrogen nuclei to combine into helium. The energy released by fusion pushed outward while gravity pulled inward, creating a long period of balance in ordinary stars. This balance is not stillness. It is a controlled exchange in which gravity supplies compression. Nuclear reactions supply heat and light, and radiation slowly leaves the star into surrounding space. Every stable star is therefore a place where matter and energy regulate each other. When that balance changes, stars evolve. Some expand into red giants, some shed outer layers, some collapse into white dwarfs, neutron stars, or black holes. Some massive stars explode and scatter newly made elements through interstellar space. The matter that later forms planets has often been shaped by these energetic endings. A rocky world like Earth requires elements that early simple matter alone could not provide in sufficient variety. Iron, magnesium, silicon, oxygen, carbon, nitrogen, and phosphorus all belong to a wider chain of cosmic processing. The existence of a planet with continents, oceans, and living chemistry depends on stellar energy from the past as well as sunlight in the present. Energy also acts through colder and less luminous forms. A cloud of gas in space may look quiet, but its future depends on temperature, density, turbulence, magnetic fields, and gravity. If heat and pressure resist collapse too strongly, the cloud can remain diffuse. If energy is lost through radiation and gravity gains influence, parts of the cloud can contract into new stars. Around young stars, disks of gas and dust exchange energy through collisions, heating, cooling, radiation, and orbital motion. Small grains stick, break, settle, and gather. Over long intervals, some become planetesimals, then planetary embryos, and eventually planets. The formation of worlds is not a single smooth act. It is a long negotiation among gravity, motion, heat, impacts, chemical composition, and the energy flowing from the young star. Matter supplies the material. Energy determines what can happen to it. The same principle continues on Earth under gentler conditions. Sunlight drives weather, climate, photosynthesis, and much of the surface biosphere. Internal heat helps drive mantle motion, volcanism, and plate tectonics. Chemical energy stored in molecules supports metabolism. None of these processes stands apart from cosmic physics. They are local expressions of the same rules that shape stars and galaxies. To explain the universe through matter and energy is therefore to connect the very large with the very small without forcing them into the same appearance. A galaxy is not like a cell, and a cell is not like a star. But each is a structured system in which matter is arranged and energy flows. The differences are enormous. The continuity is physical. Matter and energy also reveal how much of the universe remains indirectly known. Ordinary matter, the kind made of atoms, is responsible for planets, stars, gas, dust, people, and the light by which most astronomy begins. Yet ordinary matter is only one part of the cosmic inventory. Much more gravitational influence appears to come from dark matter, which does not shine, absorb, or emit light in the ordinary way. Even more of the total energy budget is associated with dark energy, the name given to whatever drives or describes the accelerated expansion of the universe. Those darker components belong to later sections, but they already affect the meaning of matter and energy here. The visible contents are not the full contents. The atoms that form every known world and organism are not the majority ingredient of the cosmos. They are the part most accessible to direct experience and light-based astronomy. This fact does not make ordinary matter unimportant. It makes it more specific. The bright, structured, chemically rich universe is a minority component, yet it is the part through which complexity, stars, planets, and life become possible. The difficulty is that matter and energy are not only things to count, they are also things to understand through behavior. A particle is known through its mass, charge, spin, interactions, and role in physical law. A form of energy is known through how it moves, transforms, gravitates, or changes a system. Light behaves as both wave and particle, depending on how it is measured. Empty space, in quantum theory, is not simply nothing, because fields still have properties even in their lowest energy states. Nuclear binding can make an atomic nucleus lighter than the separated particles that compose it, with the difference appearing as energy. Every attempt to divide the universe into simple categories eventually meets a deeper relation. Matter has structure because energy, forces, and quantum rules allow structure. Energy has consequence because matter, radiation, fields, and space-time respond to it. This is why a slow explanation of the universe cannot begin and end with objects. Objects are temporary arrangements. A star is a long event sustained by fusion and gravity. A planet is an assembled body cooling and changing through time. A galaxy is a moving population of stars. gas, dark matter, radiation, and central mass. Even an atom is not a tiny solid bead, but a stable pattern of particles and fields. Matter gives the universe form, but energy gives that form history. It allows one condition to become another, one generation of stars to seed the next, one planet to cool into a surface, one chemical pathway to persist long enough for complexity to increase. The universe is understandable not because it is static, but because its changes follow patterns. Matter and energy are the first language of those patterns. They show how a hot early state can become atoms, how atoms can become stars, how stars can become elements, how elements can become worlds, and how, in one known place, a small portion of matter can become aware enough to study the whole that produced it. The laws of physics are not rules written around the universe from the outside. They are the regular patterns found in the way matter, energy, space, and time behave. A stone falls, light bends near mass, atoms emit particular colours, planets keep to stable orbits, and stars shine for long periods because physical behaviour follows consistent relationships. These relationships can be described mathematically, tested by observation, and used to predict events that have not yet been directly seen. In a calm sense, the universe is understandable because it is not random at every level. It contains chance, especially in quantum events, and it contains disorder, especially in complex systems. But the underlying behaviour is not without structure. The same gravity that holds a person to Earth also guides the motion of the moon, shapes the paths of planets, gathers gas into stars, and helps assemble galaxies. The same electromagnetic force that allows chemistry in a cell also governs light, magnetism, electricity, and the glowing surfaces of stars. The same nuclear forces that operate inside atomic nuclei determine why stars release energy and why elements heavier than hydrogen can exist. The laws do not give the universe purpose in a human sense. They give it coherence. They make it possible for separate observations to belong to one physical account. The first and most familiar of these laws is gravity, because gravity acts on large scales and is always attractive for ordinary matter. Every mass contributes to it, and every mass responds to it. On Earth, gravity is felt as weight and falling motion. In the solar system, it becomes orbital order. Around galaxies, it shapes rotation, clustering, and the slow gathering of matter into structure. Newton described gravity as a force between masses, and that description remains highly useful where speeds are not extreme and gravitational fields are not too strong. It explains planetary motion with remarkable accuracy and still works for many spacecraft calculations. General relativity deepens this picture by describing gravity as the curvature of space-time caused by matter and energy. Under this description, planets follow paths through curved space-time, and light can be deflected by massive objects even though light has no rest mass. This is why gravity can act as a natural lens, magnifying or distorting the appearance of galaxies behind massive clusters. It is also why black holes can exist as regions where curvature creates a boundary beyond which outward paths no longer return. Gravity is the great organizer of cosmic structure, but it is also the weakest of the known forces when individual particles are compared. Its power comes from accumulation. Electric charges can cancel because positive and negative charges exist, but mass does not cancel in the same way. Over astronomical distances, gravity can add up until it dominates the movement of stars, gas, galaxies, and clusters. Electromagnetism works differently. It is much stronger than gravity on small scales, but because matter usually contains balanced positive and negative charge, its large-scale effects often become hidden or localized. Still, electromagnetism is essential for nearly everything familiar. It binds electrons to atomic nuclei, allows atoms to join into molecules, governs chemical reactions, carries light across space, and produces magnetic fields around planets, stars, and galaxies. Without electromagnetism, there would be no ordinary atoms in the meaningful chemical sense, no solid surfaces, no liquid water, no photosynthesis, no electrical activity in living tissue, and no light for telescopes to receive. Astronomy depends on electromagnetism because most direct information from space arrives as electromagnetic radiation. Radio waves, microwaves, infrared light, visible light, ultraviolet radiation, X-rays, and gamma rays are different parts of the same broad phenomenon, separated by wavelength and energy. When scientists study the color of a star, the spectrum of a gas cloud, or the redshift of a distant galaxy, they're reading electromagnetic signals shaped by atomic structure, motion, temperature, and expansion. The universe becomes visible because charged particles and electromagnetic fields interact. At smaller scales, the nuclear forces set the conditions for matter itself. The strong nuclear force holds quarks together inside protons and neutrons, and it also binds protons and neutrons into atomic nuclei. Without it, nuclei would not remain stable, and the familiar elements could not exist. The strong force is extremely powerful, but acts only over very short distances. It allows the core of a star to turn hydrogen into helium when temperature and pressure become high enough. In that process, a small amount of mass becomes energy, and the star shines. Later stages of stellar life can build heavier nuclei, and explosive or extreme environments can create and scatter many of the elements needed for rocky planets and life. The weak nuclear force is less familiar but just as important. It allows certain particles to change identity and governs forms of radioactive decay. It plays a key role in the nuclear reactions inside stars and in the behavior of neutrinos, which are very light particles that pass through ordinary matter with little interaction. The weak force helped shape conditions in the early universe and continues to operate in processes that would be impossible without it. Together, the strong and weak nuclear forces make atomic nuclei dynamic rather than merely static. They help determine which elements can form, which are stable, how stars burn, and how matter changes under extreme conditions. Motion itself follows principles that can be seen most clearly in conservation laws. Energy is not created or destroyed in ordinary physical processes, though it changes form. Momentum is conserved when systems interact. Angular momentum helps explain why collapsing gas clouds spin faster, why planets orbit, why disks form around young stars, and why rotating neutron stars can spin with extraordinary speed. Conservation laws give the universe a kind of accounting system. They do not prevent change, they organize change. When a cloud collapses under gravity, gravitational potential energy can become heat and radiation. When a star fuses hydrogen, nuclear binding energy becomes light and motion. When two galaxies interact, their stars, gas, and dark matter exchange energy and momentum in ways that reshape both systems without violating the deeper balances. These principles allow scientists to follow transformations across scales, from particles in a detector to clusters of galaxies. The same reliability also exposes where knowledge is incomplete. When observed motion seems to require more mass than visible matter provides, the conservation and gravitational framework does not simply disappear. Instead, it points toward missing ingredients, missing understanding, or both. This is part of how the dark matter problem entered modern cosmology. Physical law turns anomalies into structured questions. Quantum physics adds another layer by showing that the smaller scales do not behave like miniature versions of everyday objects. Particles are described by quantum states, probabilities, and fields. An electron in an atom does not orbit the nucleus like a planet around a star. It occupies allowed states with specific energies. Atoms absorb and emit light in precise patterns because electrons shift between these states. This is why spectra can identify elements in stars and gas clouds across enormous distances. Quantum physics is therefore not only a theory of the very small, it is one of the reasons distant astronomy is possible. It explains why matter has stable structures, why chemistry has patterns, why solids can exist, and why stars radiate in characteristic ways. It also introduces genuine uncertainty. Some outcomes can only be predicted by probability, not by exact certainty in advance. Yet this probability is not chaos. It follows strict rules that have been tested with great precision. The tension is that quantum physics and general relativity, both extraordinarily successful, are not yet joined into a complete description of gravity at the smallest scales. In ordinary stars, planets, atoms, and galaxies, the separate theories work well enough in their own domains, near the beginning of the universe, or near the deepest meaning of black holes. The separation becomes a limit. The laws beneath everything are powerful, but the deepest law may still be unfinished. This does not reduce the success of modern science. It clarifies where the edge lies. The known laws explain why the universe can have structure rather than only noise. Gravity gathers matter. Electromagnetism allows light and chemistry. Nuclear forces build and transform atomic nuclei. Conservation laws guide change. Relativity connects space, time, motion, and gravity. Quantum physics gives matter its small-scale order and its measurable spectra. Together, these ideas make a universe in which simple particles can become atoms. Atoms can become stars, stars can create elements, elements can form planets, and planets can hold complicated surface chemistry. The order is not perfect, permanent, or complete. Stars die, orbits shift, galaxies merge, particles decay, entropy increases. But even these changes occur through patterns. The universe is not controlled by visible intention, and it does not need constant adjustment to continue. Its behavior arises from consistent physical relations acting across time. That is why the laws matter so deeply in any slow explanation of the cosmos. They are not an extra topic placed after space, time, matter, and energy. They are the reason those things can form a connected history at all. What remains unresolved is whether the known laws are final, approximate, or part of a deeper structure that only appears separate because present observation has not reached far enough. For now, they provide the strongest bridge between the ordinary world and the largest cosmic questions, holding together falling stones, burning stars, bending light, silent atoms, and the widening universe within one disciplined frame. Layers of structure begin close to the familiar scale, not because planets are the center of the universe, but because they show how matter can become organized under gravity, motion, and time. A planet is a body large enough for its own gravity to pull it into a rounded shape, yet not massive enough to ignite sustained nuclear fusion like a star. Around many planets are smaller companions, rings, atmospheres, magnetic fields, or old surfaces marked by impact and internal change. In the solar system, rocky worlds occupy the warmer inner region, while giant planets and many icy bodies occupy colder distances farther from the sun. A star forms from collapsing gas. A disk around the young star supplies material for planets. Leftover debris becomes asteroids, comets, and dust. Gravity turns an untidy beginning into a system with repeated paths and long-lived relationships. The result is not perfect order. Orbits can shift, worlds can collide, moons can be captured or lost, and smaller bodies can remain as records of earlier stages. Still, a planetary system is a real structure, held together by one dominant star or sometimes by more than one star, with worlds moving inside the local reach of that gravity. Its meaning is local, but it is not isolated. The elements in its planets came from older stars, and its future depends on the changing life of its own star. The next level is the star itself, because stars are not only bright objects scattered through space, they are engines of structure. A star gathers mass, produces radiation, shapes nearby environments, and changes the chemical possibilities available to later generations. Some stars are small and dim, burning slowly for spans far longer than the present age of the universe. Others are massive, bright, and short-lived, changing quickly and ending in ways that disturb the surrounding gas. Stars often form in groups within cold molecular clouds, where gravity pulls denser regions inward until nuclear fusion begins in the cores of the new stars. The young group may remain loosely connected for a time or drift apart into the wider galaxy. Around some of those stars, planetary systems develop. Around many others, conditions may be too unstable, too crowded, or too harsh for long-lived worlds to settle quietly. A galaxy, therefore, is not simply a container of finished stars. It is a system that forms stars, loses gas, gains gas, merges with other systems, and changes its structure over time. The Milky Way contains a flattened disk with spiral structure, a central bulge, a surrounding halo, gas clouds, star clusters, and a large dark matter halo inferred from gravity. The Sun is located in the disk, far from the galactic centre, moving around the Milky Way with other stars in the local region. Within galaxies, structure appears in several forms at once. Spiral galaxies contain disks where gas and dust support ongoing star formation. Elliptical galaxies are often dominated by older stars and have less cold gas available for making new ones. Irregular galaxies have less symmetrical shapes, sometimes because of gravitational encounters or active star formation. These categories are useful, but galaxies are not fixed labels. They evolve. A small galaxy can be drawn into a larger one. Two large galaxies can pass through each other, stretch tidal streams outward, compress gas into star-forming regions, and eventually settle into a new shape. During such events, the stars themselves rarely collide because the spaces between them are so large, but gravity changes their paths and changes the gas. At galactic centers, massive black holes may grow by accreting material and by merging with other black holes. When gas falls toward one of these central objects, it can heat strongly and release large amounts of radiation before crossing inward. In some galaxies, this activity can slow or redirect star formation. A galaxy is therefore a layered system in which stars, gas, dust, black holes, magnetic fields, radiation, ordinary matter, and dark matter all contribute to behavior. It is one of the main building blocks of the visible universe, but it is already too complex to understand as a simple collection of lights. Galaxies gather into larger arrangements. The Milky Way belongs to the local group, a collection that includes the Andromeda Galaxy, the Triangulum Galaxy, and many smaller galaxies. Gravity binds this group strongly enough that its members share a common long-term relationship. The Milky Way and Andromeda are moving toward one another and are expected to merge in the distant future, not because cosmic expansion pulls them together, but because local gravity dominates over expansion at this scale. The universe expands on very large scales, but bound structures do not simply stretch along with it. Planetary systems, star clusters, galaxies, and galaxy groups remain held by gravity or other forces where those forces are strong enough. Beyond the local group are richer clusters containing hundreds or thousands of galaxies, hot gas spread between them, and large amounts of dark matter. The hot gas in clusters can be detected through X-ray radiation, showing that much ordinary matter exists outside the galaxies themselves. Gravitational lensing reveals how mass is distributed through clusters, including mass that does not emit light. Clusters are not merely bigger versions of galaxies. They are environments where galaxies move through hot plasma, lose gas, merge, and change under the influence of a shared gravitational field. The hierarchy continues, but not indefinitely in the same way. Galaxy groups and clusters arrange themselves along filaments and sheets, separated by immense voids where galaxies are much more sparse. This large-scale pattern is often called the cosmic web, a term used because matter is not spread evenly like a smooth fog. It forms connected strands and dense nodes across the observable universe. The pattern grows from tiny differences in density present in the early universe. Gravity slowly amplifies those differences. Regions with slightly more matter attract more matter. Regions with less matter become emptier by comparison. Dark matter plays a central role because it begins gathering gravitationally and provides a framework into which ordinary matter can fall. Gas follows, cools, forms galaxies, and lights parts of the structure with stars. The visible filaments are therefore only the luminous portion of a deeper mass distribution. The larger structures are not held together in quite the same way as smaller ones. Some apparent superclusters are not single gravitationally bound objects, but extended regions of related motion and density. The names given to them can depend on how boundaries are defined. A galaxy is a fairly definite object. A cluster can often be defined by a shared gravitational system. A supercluster is more difficult, because expansion may separate parts of it faster than gravity can bind the whole. On the larger scales, the universe appears broadly uniform when averaged over enough distance. The filaments, clusters, and voids are real, but they sit inside a larger pattern that has no known central point and no preferred direction in the observable region. Structure, therefore, has a limit of meaning. The universe is not organized like a set of nested boxes with one final giant object containing all others in a simple chain. Instead, it has local bound systems, larger gravitational environments, extended matter patterns, and then a scale at which the overall distribution becomes smooth enough for cosmology to describe the universe as a whole. This layered view changes the sense of location. Earth is part of the Earth-Moon system, the solar system, the local interstellar neighborhood, the Milky Way, the local group, and the wider large-scale distribution of galaxies. Each level changes what matters. For life on Earth, the Sun and planetary environment are immediate. For the origin of Earth's atoms, earlier stars and galactic chemical history matter. For the motion of the Milky Way, the local group and nearby mass concentrations matter. For the shape of the observable universe, filaments, clusters, dark matter, expansion, and early density patterns matter. No single level is the true scale of reality. Each scale reveals a different kind of organization. A moon records local impacts and tides. A star records nuclear physics and mass. A galaxy records star formation, mergers, and dark matter gravity. A cluster records hot gas, lensing, and collective motion. The cosmic web records the slow growth of structure from the early universe. The important point is not that the universe is merely large. It is that largeness is structured. Matter does not fill space in one simple way. It gathers, burns, cools, collides, separates, and aligns under physical law across many levels. The path from a planet to the cosmic web is not a climb toward importance, but a widening of context. each layer preserves some part of cosmic history and hides another. Planets preserve local chemistry and surface change, but not the full motion of galaxies. Galaxies preserve the history of stars and dark matter halos, but not every detail of the first density fluctuations. The largest maps preserve the distribution of matter, but not the small conditions that make a single world habitable. Understanding the universe slowly means moving among these levels without forcing one to replace the others. The structure of the cosmos is cumulative. It begins with the local bodies and opens outward into systems whose boundaries grow less familiar, until the visible universe becomes a connected pattern of matter, light, gravity, and empty-looking space, shaped by small beginnings that have been amplified for almost the whole age of time. The visible universe is not the same as everything that exists. It is the part of the cosmos that ordinary matter allows to be seen, measured, and interpreted through light, radiation, and the physical traces left by atoms. In this context, visible does not mean only what the human eye can detect. It includes the full range of electromagnetic signals that telescopes can receive, from radio waves to gamma rays. It also includes matter that may not shine strongly on its own, but can absorb light, scatter it, emit it when heated, or reveal itself through the way it blocks and shapes radiation from something behind it. This is the universe that first gives astronomy its images, stars and galaxies, glowing gas around young stellar regions, dust lanes across spiral arms, hot plasma between galaxies and clusters, and the faint afterglow from the early cosmos. Yet this luminous and light-interacting universe is made almost entirely of ordinary atomic matter. And ordinary atomic matter is only a small part of the total cosmic inventory. That fact changes the meaning of everything visible. The bright structures are not unimportant, but they are incomplete. They are the accessible surface of a deeper mass and energy budget that cannot be understood by sight alone. Ordinary matter is often called baryonic matter, because most of its mass comes from particles such as protons and neutrons, which belong to a class known as baryons. Electrons are also essential to atoms, though they are not baryons themselves. Together, nuclei and electrons make the atoms that form stars, planets, gas clouds, dust grains, oceans, rocks, atmospheres, and living bodies. This matter can form chemistry because electrons occupy structured states around nuclei. It can radiate because charged particles can absorb and emit energy. It can become luminous because gravity can compress it until temperature and pressure allow nuclear fusion. It can become dark in a simpler sense when it's cold, sparse, or hidden from strong radiation. A cloud of neutral hydrogen in deep space may be difficult to see in visible light, but it is still ordinary matter. A dust grain blocking starlight is ordinary matter. A planet reflecting sunlight is ordinary matter. A human body, with its carbon, oxygen, hydrogen, nitrogen, calcium, and phosphorus, is ordinary matter arranged by biology. This category contains all directly known complexity in the universe, but it does not contain most of the universe's gravitating substance. Its importance comes not from quantity, but from behavior. Ordinary matter can cool, clump, collide, radiate energy, form atoms, make molecules, and build layered structures. Dark matter, whatever its deeper identity may be, does not appear to interact with light in the same rich way. Ordinary matter does, and that interaction makes cosmic history readable. The first major visible structures are stars. Because stars turn simple atomic matter into light, a star forms when gas becomes dense enough for gravity to overcome internal pressure and bring material inward. As the core heats, nuclear fusion begins. Hydrogen nuclei combine into helium, releasing energy that moves outward and eventually escapes as radiation. That radiation crosses space and may enter a telescope after travelling for years, centuries, or billions of years. From it, scientists can infer the star's temperature, composition, motion, age, and sometimes magnetic activity. The light is not just brightness, it is a physical record. Atoms and ions in the outer layers of a star absorb and emit specific wavelengths, creating spectral lines. Those lines can identify elements because quantum physics gives each element a distinct pattern. When a star's spectrum shows hydrogen, helium, calcium, sodium, iron, or other elements, it is not a guess based on appearance. It is a comparison between measured light and known atomic behaviour. This is one of the great strengths of ordinary matter. It announces itself through patterns. Even when a star is too distant to resolve as a disk, its light can still reveal what kind of matter it contains and how that matter is moving. Galaxies extend this principle across immense populations. A galaxy's starlight carries the combined signals of many stars, while gas and dust add their own marks. Blue regions may indicate young, hot stars. Redder populations often point to older stars or dust effects, depending on context. Emission lines can reveal gas heated by young stars, shocks, or activity near a central black hole. Radio signals can trace cold hydrogen. Infrared radiation can reveal dust warmed by starlight and regions where young stars are forming inside obscuring clouds. X-ray radiation can show gas heated to extreme temperatures around compact objects, supernova remnants, or galaxy clusters. The visible universe, broadly understood, is therefore not one kind of light but a layered set of signals. Each wavelength reveals a different condition of ordinary matter. The same galaxy can look calm in one band and active in another, because cold gas, warm dust, hot stars, and energetic plasma do not speak in the same part of the electromagnetic spectrum. Multi-wavelength astronomy is a way of giving ordinary matter more than one voice, without assuming that a single image is the whole object. Much ordinary matter is not locked inside stars. In galaxies, large amounts exist as gas between stars, called the interstellar medium. This gas may be cold and neutral, warm and ionized, or extremely hot, depending on its environment. Dust, though much less abundant than gas, has an important role because it absorbs and scatters light and helps shield regions where molecules can form. In dense clouds, atoms combine into molecules, and some regions become cold enough for gravity to start building new stars. The cycle is long and uneven. Stars form from gas. Massive stars return energy and material through winds and explosions. Some of that material enriches the surrounding medium with heavier elements. New clouds form from gas that has been processed by earlier generations. Over time, galaxies become chemically more complex. This is how ordinary matter records memory. The elements in a later star system can reveal that previous stars lived and died before it formed. A rocky planet is therefore not only local material around one young star, it is part of a galactic recycling process in which atoms are heated, scattered, cooled, condensed, and assembled again. Beyond galaxies, ordinary matter appears in thinner and hotter forms. Galaxy clusters contain large reservoirs of plasma between their galaxies. This intracluster gas can be hotter than the interiors of many stars and emits X-rays. It may contain more ordinary matter than the stars in the cluster galaxies themselves. That is an important correction to the first visual impression. The eye is drawn to galaxies because stars shine, but a large fraction of ordinary matter can exist outside the bright stellar bodies, spread through enormous volumes at low density. Cosmologists have also studied diffuse gas between galaxies, some of it arranged along filaments of the cosmic web. This material can be difficult to detect because it is faint, hot, thin, or only visible through absorption lines against background sources. The visible universe is therefore partly visible by absence, by the missing wavelengths absorbed from a more distant light source. Ordinary matter does not always present itself as an object. Sometimes it is recognized as an effect on radiation passing through it. The cosmic microwave background also belongs to the story of ordinary matter, although it comes from an earlier stage than stars and galaxies. Before stable neutral atoms formed, ordinary matter existed largely as a hot plasma of nuclei and free electrons, tightly interacting with radiation. Light could not travel freely because charged particles kept scattering it. As expansion cooled the universe, electrons joined nuclei to form neutral atoms, and radiation began to move across space with far less obstruction. That radiation now appears as a cold microwave background, spread across the sky with tiny temperature variations. Those variations are small, but they are crucial because they record early density differences that later grew into galaxies and clusters. Ordinary matter at that stage was not yet arranged into stars, but it was already part of a measurable pattern. The later visible universe grew from such small differences under the influence of gravity, dark matter, expansion, and time. This connection gives ordinary matter a long history, from early plasma to neutral gas, from the first stars to enriched galaxies, from planetary systems to biological chemistry. Still, ordinary matter is a minority. Current cosmological models indicate that atoms make up only a small fraction of the total contents needed to explain cosmic behavior. Most matter is dark matter, and the largest share of the overall energy budget is associated with dark energy. This means that the part of the universe able to shine, absorb, form chemistry, and build planets is not the dominant component by mass energy accounting. It is the component that can cool efficiently, form compact objects, and produce detailed signals. There is a quieter symmetry here. The universe most directly accessible to observation is not the universe that dominates the total budget. The familiar world of atoms is richly informative but cosmically limited. It makes stars visible, galaxies traceable, and life possible. Yet it moves within gravitational structures shaped strongly by something unseen. The visible universe is therefore both a guide and a partial view. It provides the evidence from which cosmology begins, but its own motions and arrangements point beyond itself. By studying ordinary matter carefully, science discovers not only what atoms can build, but also what atoms alone cannot explain. The dark matter problem begins with motion that visible matter cannot fully explain. In galaxies, stars and gas orbit under gravity, and their speeds should reflect the mass pulling on them. If most of a galaxy's mass were concentrated where most of its starlight appears, then material far from the centre would be expected to orbit more slowly, much as distant planets in the solar system move more slowly than planets closer to the Sun. Many spiral galaxies do not behave that way. Their outer stars and gas often continue moving at unexpectedly high speeds, as if a much larger amount of mass surrounds the bright disk. The problem is not that the galaxies look unusual. The problem is that their visible matter, counted through stars, gas, and dust, does not provide enough gravity to match the observed motion. This mismatch became one of the clearest paths toward dark matter. The name does not mean a substance known in detail and simply hidden in shadow. It means matter inferred by gravity but not seen through ordinary light. It does not glow like stars, absorb light like dust, or radiate in the ways ordinary atoms usually can. It reveals itself by how other things move, how light bends, and how structure grows. The first lesson is therefore cautious and important. Dark matter is not introduced because scientists wanted to add mystery. It is introduced because several independent observations point toward more gravitating matter than ordinary atoms can provide. Galaxy rotation is only one part of the evidence. In galaxy clusters, the same kind of discrepancy appears on a larger scale. Galaxies inside a cluster move through a shared gravitational field. If only the visible galaxies and hot gas supplied the cluster's mass, many clusters would not have enough gravity to hold their observed motions together. Hot gas spread between cluster galaxies also gives evidence through its temperature and pressure. That gas can be observed through high-energy radiation, and its condition reflects the depth of the cluster's gravitational field. Again, ordinary matter is present, sometimes in large amounts, but not enough. The cluster behaves as if most of its mass is unseen. This does not make dark matter an object placed in one location. It suggests a broad distribution, often forming halos around galaxies and larger concentrations around clusters. A halo here means an extended region of mass surrounding and permeating the visible structure. The stars and gas occupy only part of the whole gravitational system. In this view, a spiral galaxy is not only a bright disk with a central concentration, it is embedded inside a larger dark matter halo that shapes its rotation and helps explain how it remains organized. Gravitational lensing provides another route to the same conclusion, and it is especially powerful because it does not depend on the brightness of the matter causing the effect. General relativity shows that mass and energy curve spacetime, and light follows paths shaped by that curvature. When a massive galaxy or cluster lies between Earth and a more distant source, the foreground mass can bend and distort the background light. The resulting arcs, multiple images, or subtle shape changes in many background galaxies allow scientists to map where the mass must be. These maps often show more mass than visible matter alone can explain. In some cases, lensing reveals dark matter distributions that are offset from the ordinary gas, making the evidence harder to dismiss as a simple mistake in counting stars. The Bullet cluster is a well-known example of this kind of separation. It appears to show two galaxy clusters that have passed through each other. The hot ordinary gas, which interacts and slows, is found in one distribution, while most of the gravitational lensing mass follows the galaxies more closely. This does not by itself identify the dark matter particle, but it strongly supports the idea that most of the mass is not ordinary gas. It behaves as if it passes through the collision with little interaction beyond gravity. That behavior is one of the central clues. Dark matter seems to attract gravitationally, but it does not appear to collide, cool, or radiate efficiently the way ordinary matter does. This is why it can form large halos without collapsing into dense disks, stars, or planets. Ordinary matter loses energy through radiation and can settle into compact structures. Dark matter appears much less able to shed energy, so it remains spread out in extended gravitational distributions. In the early universe, small density differences existed before galaxies formed. If there had been only ordinary matter interacting strongly with radiation, structure would have grown differently and more slowly. Dark matter, because it does not interact with light in the same way, could begin gathering under gravity and help guide the later formation of galaxies and clusters. The patterns in the cosmic microwave background, the distribution of galaxies, and simulations of structure formation all support a universe in which dark matter plays this early organizing role. It is not a minor correction added to the visible universe after the fact. It is part of the reason the visible universe has its observed large-scale arrangement. At the same time, dark matter remains unknown in its physical identity. It is not simply cold, ordinary material too faint to see, such as planets, dead stars, or cold gas. Such objects can exist, but they cannot account for the full evidence without conflicting with other measurements, including the abundance of light elements from the early universe and the way matter affects radiation and structure. Ordinary atoms leave signatures. There are limits on how much baryonic matter the universe can contain. Dark matter appears to require something outside the known inventory of ordinary atomic matter. Many candidates have been proposed, including new particles that interact weakly with ordinary matter, very light fields, or other possibilities still under investigation. Experiments on Earth search for rare interactions between dark matter and detectors. Telescopes look for indirect signs from space. Particle accelerators explore whether new particles can be produced under controlled conditions. So far, no dark matter particle has been confirmed. The gravitational evidence is strong, but the microscopic nature remains open. This creates a careful tension in modern cosmology. On large scales, dark matter works extremely well as part of the standard model of cosmic evolution. It helps explain galaxy clustering, the cosmic web, gravitational lensing, and the pattern of ancient radiation. On smaller scales, questions remain. Some galaxies appear to have inner mass distributions that are not always as simple as the most basic simulations predict. The number and arrangement of small satellite galaxies around larger galaxies have also been debated. Some of these tensions may be resolved by more detailed modelling of ordinary matter, because star formation, supernova explosions, gas flows, and black hole activity can reshape galaxies over time. Others may point toward more complex dark matter behaviour. The difficulty is separating a failure of simple modelling from a failure of the underlying idea. Galaxies are not clean laboratories. They are long histories of gas, stars, mergers, feedback, and environment. A dark matter theory must work not only in equations, but inside these complicated systems. There are also alternatives that try to modify gravity rather than add unseen matter. These ideas aim to explain the observed motions by changing how gravity behaves under very weak acceleration or on large scales. Some modified gravity approaches can reproduce certain galaxy rotation patterns with impressive economy. However, they face harder challenges when the evidence from galaxy clusters, gravitational lensing, the cosmic microwave background, and large-scale structure is considered together. The current weight of evidence still favours dark matter as an unseen mass component, but the existence of alternative ideas is scientifically useful. They force the dark matter explanation to keep earning its place through observation rather than habit. A strong theory should survive comparison against different kinds of evidence. Dark matter has survived many such comparisons, yet its identity has not been captured directly. That is why the problem remains alive rather than closed. It is one of the rare cases where the universe seems to give a clear gravitational answer and withhold the material explanation. The consequence reaches into the meaning of ordinary existence. Every visible galaxy may be shaped by a larger unseen halo. Every bright spiral arm, every region of star formation, every cluster of galaxies may sit inside a mass distribution that cannot be photographed in the usual way. The familiar universe of atoms is not floating freely on its own. It is moving within a darker gravitational arrangement that helped it form and continues to guide it. This does not make the visible universe less real. It makes it less complete as a map of what is there. Dark matter is not the same as absence. It is inferred presence without ordinary light. Its problem is precise because its effects are measurable, repeated, and connected across scales. The unresolved part is not whether the evidence indicates additional gravity. The unresolved part is what produces that gravity, and whether the final answer will be a new particle, a deeper field, a revised understanding of gravity, or a combination not yet clearly imagined. For now, dark matter stands as one of the strongest reminders that visibility and reality are not the same category in the universe. Dark energy enters the story through the expansion of space, not through a substance that has been collected, isolated, or directly examined in a laboratory. For much of modern cosmology, the expansion of the universe was expected to slow over time. Gravity attracts matter toward matter, so it seemed natural that the mutual pull of galaxies, clusters, gas, and dark matter would gradually reduce the rate at which cosmic distances increased. The central question appeared to be how much the expansion would slow, and whether gravity might eventually halt or reverse it. Observations of distant exploding stars changed that expectation. Certain supernovae can be used as distance markers because their brightness follows patterns that allow astronomers to estimate how far away they are. When those distances were compared with the stretching of their light, the results suggested that the expansion of the universe had not only continued, but had begun accelerating. Distant galaxies were not simply receding because of an old expansion from an early dense state. The large-scale separation between unbound regions was increasing at a rate that required a new explanation. Dark energy is the name given to that explanation, or, more carefully, to the unknown component or property responsible for the accelerated expansion. The name sounds as if it identifies a known form of energy, but it does not. It marks a measured effect whose underlying cause remains uncertain. The first important point is that expansion does not mean every object is growing larger. Earth is not expanding with the universe. The solar system is not expanding. The Milky Way is not being stretched apart by cosmic expansion in any ordinary present sense. Bound systems are held together by gravity, electromagnetism, and other local forces. Expansion becomes important on very large scales, especially between galaxy groups and clusters that are not gravitationally bound to one another. In those regions, space itself changes its scale, increasing the distances between remote systems. This is why the expansion can be observed through redshift. As light travels across expanding space, its wavelength is stretched. The farther the source and the longer the journey, the more expansion affects the light. Redshift is therefore not merely a sign of motion through space. In cosmology, it is also a sign that space has changed while the light was travelling. Dark energy enters because the pattern of these redshifts and distances indicates that the expansion history cannot be explained by ordinary matter, radiation, and dark matter alone. Something with a different behaviour must be included in the cosmic accounting. One possibility is the cosmological constant, a term that can be included in general relativity. In this view, dark energy may be a constant energy density associated with space itself. As the universe expands, matter becomes more diluted because the same amount of matter occupies a larger volume. Radiation also becomes diluted and loses energy as wavelengths stretch. A constant energy density behaves differently. If it remains present in each volume of space, then it does not fade in the same way as matter while space grows. Over time, as matter becomes more spread out, this constant component becomes increasingly important in the expansion of the universe. It does not need to push like a wind in the ordinary sense. Its effect comes from the way energy density and pressure influence space-time in general relativity. This is difficult to make intuitive, because everyday experience does not include a direct example of space carrying an energy density that affects the largest cosmic scales. Yet the mathematics of relativity allows such behaviour, and observations fit it remarkably well when a cosmological constant is included. The difficulty is that fitting the observations is not the same as understanding the source. If dark energy is the energy of empty space, then its measured value is extremely small compared with some expectations from quantum theory. This mismatch is one of the deepest unsolved problems in theoretical physics. Another possibility is that dark energy is not perfectly constant. It may be caused by a dynamic field whose strength changes slowly over cosmic time. Such models try to explain acceleration without assuming that the energy density of space is fixed forever. They're difficult to test because the differences from a cosmological constant may be small, especially with current measurements. A third possibility is that the acceleration is pointing toward a limitation in the way gravity is understood on the larger scales. General relativity has passed many tests, but most of those tests occur within systems or distances smaller than the entire observable universe. Some theories ask whether gravity might behave slightly differently across cosmic distances, producing an effect that resembles dark energy. These ideas must satisfy strict requirements. They must explain acceleration while preserving the successful predictions of relativity in the solar system, in binary stars, in gravitational lensing, and in the early universe. So far, the simplest model with a cosmological constant and dark matter remains the leading description, not because it answers every deep question, but because it matches a wide range of evidence with few assumptions. The evidence for dark energy does not come only from distant supernovae. It is also supported by measurements of the cosmic microwave background, the large-scale distribution of galaxies, and patterns known as baryon acoustic oscillations, which are ancient density features preserved in the arrangement of matter. Each kind of evidence carries different uncertainties, but together they describe a universe whose expansion history includes a transition from matter-dominated slowing to dark energy-dominated acceleration. In the earlier universe, matter played the larger role in shaping expansion and structure growth. Gravity gathered material into the web of galaxies and clusters. As the universe expanded, matter density decreased. Eventually, the dark energy component became dominant in determining the overall expansion rate. This does not erase structure that already formed. Galaxies, clusters, and bound groups continue under local gravity. But on the larger scales, acceleration changes the future. Regions not bound together become increasingly separated. Light from very distant galaxies becomes harder to receive as expansion continues. Over very long times, much of the wider universe may become less accessible to observers inside any one gravitationally bound region. The sky of the distant future would not contain the same reachable cosmic evidence that exists now. This future consequence gives dark energy unusual importance. It is not only a missing term in an equation, it affects what the universe can become and what future observers could know. If acceleration continues as a cosmological constant, distant unbound galaxies will recede beyond practical observation, leaving each bound region increasingly isolated from the larger cosmic web. Stars within galaxies will still evolve. New stars may continue forming for a time where gas remains available. Planetary systems may persist around long-lived stars, but the largest visible connections would thin as cosmic expansion carries remote structures farther from observational reach. If dark energy changes with time, the future could differ. Some models allow acceleration to weaken, others allow more extreme outcomes, though such possibilities remain speculative and constrained by evidence. The measured behavior so far is consistent with dark energy being close to constant, but precision continues to improve. Future surveys of galaxies, supernovae, gravitational lensing, and the growth of structure aim to test whether the acceleration has varied in any detectable way. The question is not only how fast the universe expands today, it is how that rate has changed across time, and what that change reveals about the underlying physics. Dark energy also changes the emotional scale of cosmology without needing dramatic language. Ordinary matter forms stars and planets. Dark matter shapes gravitational structure. Dark energy acts on the expansion of the whole observable universe. It does not build galaxies directly, and it does not form atoms, yet it dominates the current energy budget in the Standard Model. This means the largest share of the universe is associated with something known mainly through its effect on distance and time. The situation is almost the reverse of ordinary experience. The most familiar matter is a small fraction. The unseen dark matter is larger and gravitationally active. The still less understood dark energy is larger again, not as clustered mass, but as a component linked to the behavior of space itself. This layered ignorance is not a failure of science. It is the result of measurement becoming precise enough to expose what simple pictures cannot hold. A century ago, the expansion of the universe itself was not established. Later, expansion became a foundation. Then acceleration appeared inside the expansion history. Each step did not remove the previous one. It refined it and made the question deeper. The universe is not merely expanding from a hot early state. Its expansion has a changing history, and the present phase is shaped by a component whose physical nature remains unknown. That is why dark energy is one of the quiet central problems of modern cosmology. It is measured through careful evidence, it fits into successful models, and it still resists explanation at the level of cause. It asks whether empty space has a physical weight in the fate of the cosmos, whether a hidden field changes slowly across time, or whether gravity itself has another layer that appears only at the larger scales. For now, the accelerated expansion stands as a well-supported observation with an unfinished meaning. Space is not only the setting in which cosmic history happens. On the largest scales, its changing scale has become one of the main events in that history. The history of the universe begins in a state that cannot be pictured as an explosion inside empty space, because empty space in the ordinary sense is not a separate container waiting around it. The earliest known universe is better understood as an extremely hot, dense condition of space itself, filled with energy, particles, radiation, and rapidly changing fields. Present science can describe much of what happened after the first accessible moments, but the absolute beginning remains uncertain because the known laws of physics are pushed beyond their tested range. General relativity points toward an earlier state of extreme density, while quantum physics becomes essential at the smallest scales, and the two descriptions are not yet fully united. This means the first instant is not a finished chapter. It is a boundary where evidence, mathematics, and uncertainty meet. Still, from a very early time onward, the broad history becomes clearer. The universe expands as it expands. It cools. Cooling does not mean the universe enters coldness immediately. It means that the average energy of particles and radiation decreases as space grows. Conditions move from forms of matter unfamiliar to daily life toward the particles, atoms, stars, and galaxies that later become recognizable. In the earliest accessible phases, the universe is too energetic for stable atoms to exist. Particles collide constantly. Radiation is intense. Matter and antimatter appear and disappear in interactions, and for reasons not fully understood, a slight excess of matter survives. That excess becomes crucial, because without it, matter and antimatter would have nearly erased each other into radiation, leaving no later stars, planets, or living chemistry. The surviving matter is small compared with the intensity of the early radiation, but it is enough to carry the future of structure as expansion continues. The universe passes through stages in which forces separate into the forms recognized today. Particles gain the properties that allow later matter, and the balance among radiation, ordinary matter, dark matter, and space-time begins shaping the long development ahead. These early events are studied through theory and through traces left in later observations. They are not seen directly as images, but they leave consequences. The abundance of light elements, the pattern of ancient radiation, and the large-scale arrangement of galaxies all preserve information about conditions that existed before any star had formed. In the first few minutes, the universe becomes cool enough for some atomic nuclei to form. This period is called primordial nucleosynthesis. Protons and neutrons combine into the nuclei of hydrogen, helium, and small amounts of other light elements. Heavier elements do not form in large quantities at this stage because the universe expands and cools too quickly for long chains of nuclear building. The result is simple but decisive. The young universe is left with a chemical starting point dominated by hydrogen and helium. These elements later become the fuel of stars. At this early time, however, even these nuclei cannot yet hold electrons in stable atoms. The universe remains a hot plasma, with free electrons scattering light again and again. Radiation cannot travel freely across long distances because charged particles keep interrupting it. The cosmos is bright in energy, but opaque in structure. It has no stars, no galaxies, no planets, and no solid surfaces. It is a nearly smooth sea of interacting matter and radiation, with tiny density differences embedded within it. Those small differences are extremely important. They are not large enough to look like structure yet, but gravity will later amplify them. Regions that are slightly denser than average will attract more matter. Regions that are slightly less dense will become emptier by comparison. The later cosmic web begins as these very small unevennesses stretched across the young universe before anything resembling a galaxy exists. After a much longer interval, the universe cools enough for electrons to join atomic nuclei. Neutral atoms form, mostly hydrogen and helium, and light can finally travel through space with far fewer interruptions. This transition releases what is now observed as the cosmic microwave background. At the time of release, the radiation is much hotter and shorter in wavelength. Across billions of years of expansion, it is stretched into microwaves and cooled to a faint glow spread across the sky. This background is one of the most important records in cosmology because it shows the universe at a time before stars. Yet after atoms become stable, its tiny temperature variations reveal the seeds from which later structure grows. After this, the universe enters what is sometimes called the cosmic dark ages. The phrase simply means that there are no stars yet to produce visible light. Space contains mostly neutral hydrogen and helium, along with dark matter and radiation fading through expansion. Gravity continues its slow work. Dark matter gathers first into larger halos because it does not interact with radiation in the same way ordinary matter does. Ordinary gas falls into these gravitational wells, compresses, cools, and eventually reaches conditions where the first stars can ignite. The first stars are expected to be different from many stars seen today. They form from gas almost entirely lacking heavy elements, because earlier stars have not yet made and scattered those elements. Without heavier elements, the gas cools differently, and the first stars may often be massive, hot, and short-lived. Their light begins to change the universe around them. Ultraviolet radiation from early stars breaks apart neutral hydrogen, gradually rionizing much of the gas between galaxies. Their deaths enrich space with the first heavier elements, allowing later generations of stars to form with more complex chemistry. This is a major change in cosmic history. The universe moves from a simple chemical state to one capable of producing carbon, oxygen, silicon, iron, and many other elements. The first galaxies grow as stars gather within dark matter halos. Gas continues falling inward, and small systems merge into larger ones. Galaxies are not born fully formed. They assemble through repeated episodes of star formation, gas flow, gravitational interaction, and merging. Some become rotating disks, Some become more rounded systems. Some remain small and irregular. Central black holes grow in many galaxies, sometimes feeding on surrounding material and producing powerful radiation. Over time, the universe becomes more structured and chemically richer. New stars form from gas already touched by older stars. Planets become increasingly possible because dust and heavier elements are now available. Around some young stars, disks of material settle into the early stages of planetary systems. Small grains gather into larger bodies. Collisions build worlds. Volatile materials, metals, silicates, and ices sort themselves according to temperature, distance, and local history. The solar system forms much later than the first stars, from material already enriched by earlier stellar generations. Earth forms as part of this local process, not at the beginning of the universe, but after enough cosmic time has passed for the necessary elements to exist in one region of a galaxy. The Sun is therefore a later generation star, and Earth is a later generation planet. Its rocks, oceans, atmosphere, and living systems depend on a universe that had already spent a long time making and redistributing matter. Cosmic history continues after planets form. Stars keep being born where cold gas remains. Older stars die and return material to space. Galaxies merge and reshape one another. Clusters gather galaxies and hot gas inside dark matter structures. The cosmic web becomes more pronounced as gravity amplifies early density differences. Yet the rate of star formation across the universe does not remain constant. It rises, reaches a broad peak when the universe is younger, and then gradually declines as gas is consumed, heated, expelled, or locked into long-lived stars. The present universe is still active, but it is quieter than its most productive era of star formation. At the same time, dark energy has become more important in the overall expansion, as matter becomes more diluted by expansion. Dark energy dominates the large-scale behavior of space. The growth of new structure slows on the larger scales. Bound galaxies and clusters remain together, but distant unbound regions separate more quickly. The universe has therefore changed not only in contents, but in character. It begins hot, dense, smooth, and opaque. It becomes transparent, dark, structured, luminous, chemically rich, planet-forming, and eventually dark energy dominated. Each stage follows from previous conditions, but none is a simple repetition of the last. The long future remains less certain in detail, but if current acceleration continues, distant galaxies beyond the local bound region will become increasingly difficult to observe. Star formation will decline as usable gas runs low. Long-lived stars will continue shining for immense spans, while more massive stars vanish much sooner. Over still greater intervals, stellar remnants, black holes, cooled planets, and thin radiation may dominate the scene. This future is not close on human or even geological timescales, but it follows from the same slow changes already visible in cosmic history. The universe is not a static arrangement of objects. It is a sequence of physical eras, each one shaped by expansion, cooling, gravity, matter, radiation, dark matter, dark energy, and the laws that connect them. To trace that sequence is to see that the present moment is not the natural center of the story. It is one stage in a much longer unfolding, late enough for galaxies, planets, and life to exist, but early enough that the evidence of the young universe is still visible across the sky. Earth occupies a small position in the universe, but smallness is not the same as meaninglessness. It is one rocky planet orbiting one ordinary star, inside one galaxy among many. Yet it is also the only known place where matter has organized itself into oceans, continents, atmosphere, living cells, memory, technology, and scientific inquiry. Both facts have to remain together. If Earth is described as central, the description fails because the universe does not arrange itself around this planet. If Earth is described as insignificant, that also fails because the history of the universe has produced at least one world where part of the cosmos can examine its own origin. The calm position is more precise. Earth is not the centre of the universe. It is a local outcome of cosmic history, formed from ordinary matter inside a later generation planetary system, shaped by the life of the Sun, the structure of the Milky Way, and the long chemical work of earlier stars. Its importance is not astronomical dominance. Its importance is that complexity becomes observable here from the inside. The planet forms about 2/3 of the way through the universe's present age, long after the first stars and galaxies appear. By then, space has already been enriched with heavier elements made in stellar interiors and violent stellar endings. The early universe provides mostly hydrogen and helium, but Earth requires much more. Its rocks need silicon, oxygen, magnesium, iron, aluminum, calcium, and other elements. Its oceans and atmosphere require volatile compounds shaped by planetary formation, impacts, volcanic release, and later biological change. Its living systems depend on carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, metals, liquid water, energy flow, and stable enough conditions for chemistry to persist. These ingredients do not appear all at once. They are inherited from a chain of cosmic and planetary processes. The atoms in Earth are older than Earth. Many were made before the solar system existed, then gathered into a rotating disk around the young Sun, where dust and gas slowly assembled into larger bodies. Earth begins as one object among many in that disk, growing through collisions, heating, differentiation, and cooling. Heavy material sinks inward to form a metallic core. Lighter rocky material forms the mantle and crust. Impacts reshape the surface. Internal heat drives long-term geological change. The Moon likely forms after a major impact early in Earth's history, and its presence affects tides, rotation, and the long stability of the planet's axial behaviour. None of this makes Earth unique by simple category. Rocky planets are expected around many stars. Large impacts are common in forming systems, atmospheres, volcanoes, magnetic fields, oceans, and moons may occur in many combinations elsewhere. What remains unknown is how often these conditions combine into a world that remains habitable for long spans. Habitability is not one property. It is an ongoing balance among star, orbit, atmosphere, interior, surface water, chemistry, and time. Earth orbits within a distance range where liquid water can persist on the surface under the right atmospheric conditions. But distance alone is not enough. Venus and Mars show why. Venus is closer to the Sun and has a thick atmosphere that traps heat strongly. Mars is farther away, smaller, colder, and has lost much of its early atmosphere and surface water stability. Earth remains between these outcomes because of many linked factors, including its size, internal activity, magnetic environment, water cycle, carbon cycle, and biological feedbacks. The planet is not perfectly stable. It has passed through severe climate shifts, mass extinctions, changing continents, changing atmospheres, and long intervals when life was mostly microscopic. Its habitability is a history, not a fixed gift. Life does not appear in the fossil record as a sudden complex world. It begins with simple organisms whose origins remain uncertain in detail. Early life changes slowly, then profoundly. Microbes alter chemistry, including the gradual oxygenation of the atmosphere through photosynthesis. Oxygen allows new forms of metabolism, but it also transforms the surface environment in ways that are dangerous to organisms adapted to earlier conditions. Later, complex cells, multicellular organisms, plants, animals, and eventually human beings appear through biological evolution. This process is local, contingent, and physical. It does not require Earth to be cosmically privileged. It requires that one planet maintained enough continuity for evolutionary history to accumulate. Human beings arrive very late in Earth's story, and Earth arrives late in cosmic history compared with the first stars. The scale difference is large enough to correct any easy sense of centrality. The Milky Way was forming stars long before the solar system existed. The universe was expanding, cooling, and building galaxies for billions of years before Earth became a planet. Life spent most of its time in microscopic forms before anything like human awareness appeared. Modern scientific civilization occupies only a brief interval compared with geological time. This does not diminish the value of inquiry. It gives inquiry its proper scale. Human knowledge is young, local, and incomplete, but it is not detached from the universe it studies. The elements in human bodies, the light-entering telescopes, the radio signals used to map gas, and the minerals in instruments all belong to the same physical inventory. Science is not an outside commentary on the cosmos. It is a process occurring within one small part of it, using matter to understand matter, and using patterns in evidence to reconstruct places and eras far beyond direct experience. Earth's location also shapes what can be known. The solar system lies in the disk of the Milky Way, not near the galactic center and not in the empty space between galaxies. This position gives access to a relatively quiet stellar neighborhood compared with denser regions, though not a perfectly isolated one. The atmosphere protects the surface from much harmful radiation, while blocking some wavelengths that astronomers must observe from space or high altitudes. The rotation of Earth, its orbit around the Sun, and the motion of the solar system through the galaxy all affect observation. Every measurement is made from a moving platform inside a planetary environment. Even so, the universe leaves enough signals to be studied. Light from distant galaxies reaches Earth after crossing expanding space. The cosmic microwave background reaches instruments as a record from the young universe. Meteorites preserve early solar system chemistry. Lunar rocks preserve impact history. Mars, Venus, asteroids, comets, and outer moons provide comparisons that make Earth easier to understand. Earth is not studied properly when isolated from its neighbours. It becomes clearer as part of a planetary system, a stellar environment, a galaxy, and a cosmic history. The search for life elsewhere arises naturally from this context. Since Earth is made from common elements and orbits an ordinary star, it is reasonable to ask whether life has also appeared on other worlds. Thousands of planets have been found around other stars, and many more are expected. Some are gas giants, some are rocky candidates, some orbit close to their stars, and some lie in regions where surface liquid water might be possible if other conditions are suitable. Yet habitability is easier to define broadly than to confirm remotely. A planet's size, mass, orbit, atmosphere, star, magnetic environment, geology, and history all matter. Even if a planet appears promising, evidence for life is difficult to separate from non-living chemistry. Earth therefore becomes both an example and a warning. It shows that life can arise in the universe, because it has happened here. It does not show that life is common, because one known example cannot establish a frequency. The same caution applies to intelligence and technology. Human beings prove that a planet can produce observers capable of cosmology, but they do not prove that technological civilizations are widespread or long-lasting. Earth's role in the full picture is therefore balance between humility and evidence. It is not the goal toward which the universe was obviously moving. The laws of physics do not mention planets with life as a required outcome. Most of the universe is hostile to human biology by ordinary standards. Intergalactic space is thin and cold. Stars are hot and destructive at close range. Many planets are frozen, scorched, airless, crushed by pressure, or chemically unsuitable for known life. Even Earth is habitable only in a narrow surface layer, protected by systems that have changed over time and could change again. Yet the universe is also not sterile in all places by necessity. It makes atoms, molecules, dust, planets, oceans, and energy gradients. It allows stable stars and long intervals. It allows complexity to persist where conditions remain favourable. Earth is the proof that cosmic processes can produce not only structure, but interpretation. It is a small world within a vast system, and from that small world the vast system becomes partly knowable. The proper conclusion is neither pride nor dismissal. Earth is local, fragile, chemically rich, historically shaped, and scientifically precious. Humanity is not outside the universe looking in, and not the measure of all that exists. It is one recent form of matter able to ask how matter became stars, planets, life, and thought. In that limited but real sense, Earth is a witness point inside the larger history, not central to the universe, but central to the only confirmed understanding of it so far. The remaining questions in cosmology are not empty gaps placed beyond knowledge. They are pressure points created by knowledge becoming more exact. The universe is now understood well enough for its uncertainties to have shape. It expands. It contains ordinary matter, and dark energy. It has a history that runs from a hot early state into atoms, stars, galaxies, planets, and life on at least one world. It follows laws that work with great precision across many scales. Yet the same model that organizes so much also points toward places where explanation is incomplete. The first of these is the question of origin. The hot early universe is strongly supported by evidence, but the phrase does not automatically explain why there was a universe in that condition, why expansion began, or whether the word before has any meaning when time itself is part of the system. Physics can describe the universe back toward extremely early moments, but near the deepest beginning the known theories meet their limits. General relativity treats space-time as smooth and dynamic. Quantum physics treats the small-scale world through fields, probabilities, and discrete interactions. At the earliest energies, both descriptions appear necessary, but they do not yet merge into a single tested theory. This makes the origin question different from a missing detail in a timeline. It may require a deeper account of what space and time are. Some ideas propose inflation, a very rapid early expansion that could explain why the observable universe is so uniform on large scales, and why its geometry appears close to flat. Inflation is powerful because it connects several observed features under one possible mechanism, but its precise nature is not settled. What field drove it, how it began, how it ended, and whether it implies regions of universe beyond the observable one remain open questions. Other approaches ask whether the beginning was a bounce from an earlier concreting phase, a quantum transition, or something for which ordinary language has no simple image. None of these possibilities can be accepted only because it sounds elegant. Each has to face evidence, and the available evidence from the earliest times is limited. The The cosmic microwave background, the abundance of light elements, gravitational waves if detected from early processes, and the distribution of matter all act as partial records. They do not yet reveal the first cause, if first cause is even the right category. A second unresolved question concerns the dark components that dominate the present cosmic inventory. Dark matter behaves like gravitating mass, helps structure form, and appears across many independent observations, yet its particle or field identity remains unknown. Dark energy shapes the accelerated expansion, yet it may be a cosmological constant, a dynamic field, a sign of modified gravity, or something not yet described clearly. These are not small additions to an otherwise complete picture. Together, they make up most of the standard cosmic accounting. The difficulty is that their effects are large while their direct physical nature is hidden. Dark matter can be mapped by gravity, but not yet held in a detector as a confirmed new particle. Dark energy can be measured through cosmic expansion, but not yet explained as a familiar substance. The universe has given behavior before identity. This situation is uncomfortable in a useful way. It prevents cosmology from becoming a story only of visible objects. It forces every map of stars and galaxies to include an unseen scaffolding, and every history of expansion to include a component tied to the nature of space itself. A third question lies in the relationship between gravity and quantum physics. Each theory has succeeded so well in its own domain that their conflict becomes more important, not less. General relativity describes the large-scale structure of space-time and the gravitational behavior of planets, stars, galaxies, black holes, and the expanding universe. Quantum theory describes particles, atoms, fields, radiation, chemistry, and the small-scale processes that make stars shine and matter stable. But black holes and the earliest universe bring both domains together. Inside the mathematical description of a black hole, gravity becomes extreme. Near the beginning of the universe, density and energy become extreme. In these conditions, a theory of quantum gravity may be needed. The problem is not only technical, it reaches into the meaning of space, time, information, and causality. Black holes appear to have temperature and entropy, which suggests that gravity, quantum theory, and information are linked more deeply than classical physics alone would imply. The unresolved question is what space-time is made of, if made of is even the correct phrase. It may be fundamental. It may emerge from more basic relations. Present science has strong candidate ideas, but no final experimental confirmation. The edge remains real because the evidence is difficult to reach. Another question concerns the shape and extent of the universe beyond the observable horizon. Observations indicate that the observable universe is close to spatially flat and broadly uniform on the largest measured scales. But the observable horizon is not a physical boundary where existence must stop. It is the limit imposed by the age of the universe, the speed of light, and the expansion of space. Beyond it, there may be more universe similar to the region that can be observed. There may be far more than can ever be reached by signals. Some inflationary ideas even suggest a much larger structure with regions that differ in conditions, though such claims become difficult to test. The question of total size, overall topology, and whether the universe is finite or infinite remains unsettled. A finite universe need not have an edge in the ordinary sense, just as a surface can be finite without a border. The cosmic geometry is not simply a surface in space. An infinite universe creates its own conceptual difficulties, not because infinity is impossible in mathematics, but because physical infinity is hard to confirm from inside a limited horizon. The measured region is immense, but immensity is not the same as totality. The fate of the universe is also open in detail, though current evidence points toward continued accelerated expansion. If dark energy remains constant, distant unbound galaxies will move beyond practical observation, star formation will decline, and the cosmos will gradually become colder, darker, and more dilute. If dark energy changes, the future could be different. It might weaken, alter the expansion history, or in extreme models grow stronger with disruptive consequences. The fate depends on what dark energy is, how matter behaves over immense times, whether protons decay, how black holes evaporate, and whether any new physics appears beyond present theory. These questions extend far beyond human timescales, but they are still physical questions. They ask what long-term change means in a universe governed by expansion, entropy, gravity, and quantum effects. The possible futures are not prophecies. They are conditional paths built from present evidence and present uncertainty. A final group of questions concerns life and mind. Earth proves that the universe can produce biology and observers. It does not reveal how often this happens. The ingredients for life appear widespread in some forms. Organic molecules exist in interstellar clouds, protoplanetary disks, comets, meteorites, and planetary environments. Planets are common around stars. Water appears in many cosmic settings, yet life is not guaranteed by ingredients alone. It requires pathways that concentrate, preserve, and organize chemistry across time. It also requires planetary conditions stable enough for evolution, but active enough to supply energy and chemical exchange. The origin of life on Earth remains incompletely understood, and without that understanding, estimates of life elsewhere remain uncertain. Intelligent technological life is a still narrower question. It depends not only on biology beginning, but on long evolutionary histories, environmental continuity, chance events, and perhaps many filters not yet known. The silence of the sky does not settle the issue. It may reflect distance, rarity, timing, limits of detection, or assumptions about what signals should look like. The search remains scientific when it stays tied to evidence rather than desire. These remaining questions do not break the larger explanation of the universe. They show where the explanation is still growing. A mature scientific picture can be both successful and unfinished. It can describe the expansion history while not knowing the deepest cause of expansion. It can map dark matter while not knowing its identity. It can use space-time while not knowing whether space-time is fundamental. It can place Earth in cosmic context while not knowing whether life is common. The universe, explained slowly, does not end with complete possession of the subject. It ends with a clearer distinction between what is known, what is inferred, what is plausible, and what remains beyond present reach. That distinction is part of the calm strength of science. It does not require pretending that mystery has vanished, and it does not need to enlarge mystery beyond the evidence. The universe remains open at its deepest edges, but the edges are not vague. They are marked by observations, equations, instruments, failed searches, successful predictions, and questions precise enough to guide the next search. The universe remains larger than any single explanation, but it is not beyond careful thought. It can be approached through the steady pieces that evidence allows space and time, matter and energy, gravity and light, atoms and stars, galaxies and expansion, visible structure and hidden influence. Each part gives the whole a firmer outline, even when the outline does not close completely. The universe is not only a distant subject filled with remote objects. It is the physical history that made every local thing possible, including the small world from which that history is studied. Its earliest accessible state still carries unanswered questions. its dark matter still gives gravity without revealing its identity. Its dark energy still shapes the widening distance between unbound regions without yielding a simple cause. Its future still depends on physics that may not yet be fully known. And yet, within those limits, the picture is already deep and coherent. A hot young cosmos becomes transparent. Small density differences become structure. Stars make elements. Galaxies gather and change. Planets form from older material. On one planet, chemistry becomes life, and life eventually becomes a way for the universe to measure its own past. The remaining mystery does not erase the knowledge. It gives the knowledge edges. It shows where evidence ends, where inference begins, and where the next question has to be placed with care. In that quiet balance, the universe can be understood as both familiar and unfinished, made of the same atoms that form ordinary things, shaped by forces that can be tested, and still open at scales and depths far beyond present reach. The explanation rests there, not as a final closing of the subject, but as a calm stopping point inside a much longer search.